13.7 billion years ago, the Big Bang happened, but what happened before that? And as the title suggests, what exactly is meant by this before the big explosion? Can we even talk about a before when time itself began with the Big Bang? To put it into perspective, just think about the time of dinosaurs. We weren't there, but today we know they existed before us. Similarly, today, we have a wealth of evidence for the Big Bang, and intriguing theories about what happened before that. To better understand the first theory about what happened before the Big Bang, let me ask you something first. Would you believe it if I told you that once upon a time, the entire Milky Way and other galaxies were smaller than a seed? According to the traditional view, before the Big Bang, all matter and energy were compressed into an incredibly tiny space from the point of singularity. This means that the Big Bang originated from a very small point with infinite density and temperature. This point is where everything we know, all the galaxies, stars, and even the smallest particles came from as the universe expanded. It's hard to imagine a point where the laws of physics as we know them don't apply. The concept under discussion is known as the singularity, and it's the most fundamental and widely accepted idea about the pre-Big Bang universe. Major scientists, including Stephen Hawking, Ray Kurzweil, and Roger Penrose, support this theory. However, some scientists have different ideas that don't rely on a singularity. For example, loop quantum gravity suggests that the universe doesn't just begin from one spot and keep expanding forever. Instead, it proposes that the universe goes through cycles of expanding and then bouncing back. Instead of a big dramatic ending, this theory suggests that the universe keeps bouncing back each time it gets close to the edge, like a cosmic trampoline keeping it going. Then there's M theory, suggesting our universe is just one of many in a multiverse, likely springing into existence from quantum fluctuations. Quantum fluctuations are quick changes in energy happening in tiny particles, sometimes causing new particles to pop into existence briefly before disappearing again. M theory explains that the particles we observe are tiny, vibrating strings existing in more dimensions than we're used to. Don't freak out just yet. Think of these strings as guitar strings that, when plucked, vibrate to produce particles and forces in our universe. These strings are incredibly small and undetectable directly, yet their vibrations manifest everything we experience. The multiverse concept expands on this, proposing many other layers of reality, each a different universe sparked into being by minute. These ideas are trying to solve the problems that come with thinking everything came from a small dot. We learned about all of these things through the CMB, or cosmic microwave background radiation, which is like the universe's lingering glow from the Big Bang. The CMB is seen as stable because it consistently shows up as a faint glow in the microwave spectrum and looks pretty much the same, no matter where you look in the sky. But even before these stable microwave radiations or any other matter made of atoms or molecules existed, the universe was already busy at work. Around 1/10,000th of a second, 0.0001 seconds, after the Big Bang, protons and neutrons, which make up atomic nuclei, emerged. This was a significant step towards the complex matter we're familiar with today. Going even further back to a time before stable matter as we know it, the universe was in a state known as the Grand Unified Epoch. This period is fascinating because it predates the formation of protons and neutrons, featuring instead a sea of elementary particles, including quarks, which are the building blocks of protons and neutrons. According to physical cosmology, if we assume the universe is described by a grand unified theory, this epoch followed the Planck epoch, beginning around 10 to the power of -43 seconds before the Big Bang. At this point, the universe's temperature was incredibly high, even by cosmic standards, matching the temperatures predicted by grand unified theories, over 10 to the power of 27 Kelvin. During the Grand Unification Epoch, which lasted until about 10 to the power of -36 seconds after the Big Bang, the universe was under conditions where 3 of the 4 fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, were merged into a single force known as the electronuclear force. Gravity had already separated from this unified force at the end of the Planck epoch. In such extreme conditions, concepts like mass, charge, and other particle properties were not applicable in the way they are in the cooler, more structured universe we observe today. The Grand Unified Epoch is often discussed in conjunction with the concept of the pre-Big Bang because it represents a period very close to the beginning of the universe, just after the Planck epoch, which is the earliest known measurable period of time. After determining the timeline back to the Grand Unified Epoch, Researchers are intrigued to discover the foundational elements of the cosmos. Yes, just as cells are the building blocks of your body, don't you think the universe might also have its own fundamental building blocks? Indeed, it does. And these elements even existed long before the Big Bang. The standard model of particle physics explains it well and sorts all known elementary particles into specific groups. These include fermions, like quarks and leptons, and gauge bosons, such as photons and WZ bosons, which are the fundamental components of matter. This framework helps us understand everything in the universe, from the air we breathe to the stars twinkling in the night sky. Quarks are minuscule particles that join together to form protons and neutrons, the heart of atomic nuclei. There are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. A fascinating aspect of quarks is their inability to exist alone due to color confinement, meaning they're always found in pairs or trios, making up mesons and baryons respectively. For example, a proton is composed of 2 up quarks and 1 down quark, whereas a neutron is made up of 2 down quarks and 1 up quark. The interactions and properties of quarks are governed by the strong nuclear force, which is the most potent of the 4 fundamental forces, keeping them tightly bound within the nucleus. Electrons circle the atom's nucleus, playing a key role in chemical reactions and conducting electricity. Neutrinos, on the other hand, are ghostly particles that barely interact with matter, making them incredibly challenging to detect, even though they are produced in vast numbers by the sun and other nuclear phenomena. But just as sometimes 2 of your colleagues might argue over an idea, one saying it should be included, the other dismissing it as rubbish, scientists also have their debates. In this case, half of them believe that protons and electrons existed long before the Big Bang in some form, while the others argue they appeared later. However, there's one element on which both groups agreed, and that is leptons. Leptons form another group of fundamental particles. There are 6 flavors of leptons as well: the electron, muon, tau, and their respective neutrinos: electron neutrino, muon neutrino, and tau neutrino. In contrast to quarks, leptons do not feel a strong nuclear force. The standard model also describes bosons, the force carriers that mediate the 4 fundamental forces. Photons are responsible for the electromagnetic force, gluons carry the strong force, W and Z bosons manage the weak force, and the Higgs boson is connected to the Higgs field, which endows particles with mass. The standard model provides a framework for extensions and modifications to explore the conditions that might have led to the Big Bang. And just like humans look for soulmates to share their lives with, it turns out that particles from the standard model have their own romantic side too. They apparently crave partners just like we do. While digging into this, I found the theory of supersymmetry, or SUSY for short. It's a bit like particle dating. It suggests that every particle around before the Big Bang had a super partner. Imagine that. These particle pairs eventually embraced in a cosmic hug and collapsed together. And poof, they transformed to create something entirely new. Quite the romantic drama, isn't it? Well, let's be serious. So the reality of supersymmetry is that it aims to bridge some of the gaps and unresolved questions left by the standard model, including the nature of dark matter, the puzzle of the hierarchy problem, and the quest for a unified theory of all fundamental forces, including gravity. For example, in supersymmetry, each fermion, a particle like an electron or quark, would have a corresponding boson superpartner and vice versa. This includes particles like the gluino, which would be the superpartner to the gluon, and the gravitino associated with the graviton, hypothetically responsible for gravity. These superpartners have yet to be observed, but their existence would have profound implications for our understanding of the universe, offering potential solutions to long-standing problems and mysteries. The idea of supersymmetry also ties in with other advanced theoretical frameworks, such as string theory. Furthermore, supersymmetry and string theory hint at the exciting possibility of additional spatial dimensions beyond our familiar 3-dimensional space. These hidden dimensions, though beyond our current sensory experience, could be integral to the structure of the universe and the fundamental forces that govern it, including the mystery of why gravity is so much weaker than the other fundamental forces. Now, would you mind if at this point I tell you the Big Bang was not the beginning of everything? Well, it's not just me saying this. There's a theory that tries to prove it. But how is that even possible? And what speculations support it? First, Let's understand the Big Bounce hypothesis. This theory suggests that the Big Bang was just a phase in an ongoing cosmic cycle. Before the Big Bang, there was a universe that eventually collapsed into a singularity, an infinitely dense and small point. From this point, the universe didn't just explode, it bounced back, starting a new expansion phase that we call the Big Bang. This model proposes that the universe goes through cycles of expansion, Big Bang, contraction, Big Crunch, and then another bounce. One fascinating part of the pre-Big Bang theory is the unexpectedly low entropy observed in our universe. Entropy is essentially a measure of disorder or randomness in a system, and it typically increases over time. However, the early universe was highly ordered, having surprisingly low entropy. Why does this matter? Well, a solid pre-Big Bang theory needs to explain this irregularity, and that's where the Big Bounce theory comes into play. It challenges the idea of a single origin by suggesting the universe cycles through phases of high and low entropy, offering a refreshing alternative to the traditional Big Bang narrative. The Big Bounce theory addresses what might have existed before the Big Bang. Instead of a one-time beginning, it suggests our universe has experienced multiple cycles of expansion and contraction. During the contraction phase, or the Big Crunch, the universe collapses, pulling all matter and energy toward a central point. This point, or singularity, bridges the previous universe with the next cycle, leading to another Big Bang. Although the details of what happens during each bounce are still theoretical, the Big Bounce offers a fascinating alternative to the traditional Big Bang model, suggesting our universe might have been part of an eternal cosmic cycle before the collision. Similar to this one, there are some more scientists who really turned our universe's story upside down with their theories, like the cyclic ekphorotic universe theory. Now that is a brain scrambler. It described our universe as a four-dimensional brain within a higher dimensional space. Periodically, our universe collided with a neighboring parallel universe. These weren't just casual bumps. They were cosmic smackdowns that reset our universe in massive bounces, sparking new cycles of expansion, much like what we attribute to the Big Bang. As our universe stretched out, it also cooled off and began to drag, slowing down until gravity pulled everything back together towards another monumental crash. It was like the universe was on a cosmic yo-yo, endlessly spinning out and reeling back in. Each crash mixed energy and matter between these brain worlds, kickstarting another round of expansion and cooling, ekpyrotic, which points to the scorching heat generated in these collisions, summed up the fiery drama of it all. What was really cool about this theory was that it skipped the whole singularity snag where traditional physics got all muddled up. No mysterious start point here, just an ongoing cosmic cycle. And it wasn't just spinning its wheels. This theory aimed to solve some of the stickiest cosmic mysteries, like why the universe seemed so uniform, how the matter was spread around, and what was up with dark matter and dark energy. Quite the storyline, right? Who needed a singular beginning when you had an eternal cosmic dance? Hearing about these wild theories that claim there was no Big Bang, just endless cycles of expansion, might have you scratching your head in disbelief. But before we go any further, you might want to sit down if you're standing. Trust me, you'll need the support for what's coming next. So there's this group of top scientists who've introduced something called the holographic principle. Chances are, you've definitely heard the debate about whether the Earth is flat or round. But get this. These brilliant minds actually believe the entire universe started as a flat, two-dimensional plane. Yes, you heard right. There was a flat universe that existed pre-Big Bang and that magically popped into 3D. This isn't your usual conspiracy. It's actual science proposed by the Dutch physicist Gerard 't Hooft, and later refined by American physicist Leonard Susskind. They suggest that everything you see, touch, and experience in 3 dimensions can be described completely by a 2-dimensional surface. Imagine that every 3D movie you've watched is actually just a clever projection from a flat screen. That's the universe they're talking about. So how does this all tie into the brain-melting realms of string theory and quantum gravity? Quite significantly, it turns out. The holographic principle plays a key role by proposing that a volume of space can be represented entirely on its boundary. Think of it like the ultimate save file for a video game. Everything happening in the game can be stored on the edge of the universe's playing field. This idea isn't just cool, it has serious implications for black holes too. According to the holographic principle, the information about everything that ever falls into a black hole could be stored right on its edge. This means the maximum entropy, or level of disorder, depends not on the volume of the black hole, but on its surface area. One of the most fascinating examples of this principle at work is the ADS through CFT correspondence. This theory connects two completely different types of physical theories, one describing a universe with negative curvature, ADS, and another describing physics on the boundary of such a space, CFT. It's like saying you can understand what's happening inside a balloon by studying just the surface. And what about the beginning of everything? The Big Bang. Here's where it gets even wilder. Holographic principle suggests that our 3D universe could actually be a projection from this 2D information. This insight gives us a brand new way to think about what happened before and during the Big Bang. Was our universe just a 2D area waiting to bloom into 3 dimensions? While this all might sound like something straight out of a science fiction novel, researchers are actively looking for evidence to support these ideas, studying cosmic microwave background radiation to detect holographic clues about the universe's true nature. After all this detail, you might be feeling a bit information saturated, but if there's still a lingering question in any corner of your heart, don't hesitate to sink it in the comments section, or whatever you want to do.